Bent shafts fall primarily into two categories with very differing phase characteristics. One is a bend in the rotor between the bearings. The other is a bend in the rotor at the coupling. A rotor which is bowed between the bearings actually has an unbalanced condition, but exerts axial force on the bearings. The bend causes one side of the rotor to be longer than the other, forcing the bearings out during part of the rotation and lets them flex in for part of the rotation. This makes it appear as if the ends of the shaft are moving in opposite directions, while for a straight shaft the ends are moving together. The phase data for a bent shaft, then, will be 180 degrees out in the axial direction from one end of the shaft to the other. Be sure to account for the direction of the sensor. Because of the axial movement associated with a bent shaft, the axial direction provides the most information. 4 other axial measurements should be made. Assuming a clock face over the end of the bearing or machine, the measurements should be made at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock positions. A cocked bearing will exhibit approximately a 180-degree difference from the 12 o'clock position to the 6 o'clock position. 180-degree phase shift will also be present from the 3 o'clock position to the 9 o'clock position. Again, these measurements are normally within 30 degrees. When a shaft is bent at the coupling end, it moves in the same way as a combination of angular and offset misalignment condition. The phase data will have a 180-degree change across the coupling in vertical to vertical or horizontal to horizontal measurements. The axial measurements across the coupling may have any phase relationship depending on the coupling type and the amount the shaft is bent. A bearing cocked on a shaft has the same phase characteristics as a shaft that is bowed between the bearings. As the shaft rotates, it tends to force the cocked bearing to correct its position. Because it cannot be forced into a correct position, the bearing can actually force a bend in the shaft and exhibit characteristics similar to a bent shaft. The axial direction will produce phase data 180 degrees out from side to side or top to bottom of the bearing. Mechanical looseness can exhibit both directional and erratic phase characteristics. The directional phase is associated with loose bolts, mountings, base plates, and other non-rotating components. Erratic phase readings are normally associated with looseness in the rotating elements. When a component is loose at the mounting positions, the foot tends to hammer against the bolts and the base plate. Measure the phase on the bolt, the foot, the base plate, and even the floor to determine the movement. A loose mounting produces a 180-degree phase shift from the bolt to the foot, from the foot to the base plate. If there is no phase shift between two of the components, such as the floor to the base plate, there is not a looseness problem there. Erratic or unstable phase measurements can be associated with rotating element looseness. During normal phase measurements, if the phase is very unsteady, not simply slowly rotating or staying within a certain window, then check the spectrum for peaks near the 1x peak and verify that the bandwidth is narrow enough to include only the 1x peak. Also check for a looseness spectral pattern, that is, multiple harmonics of the turning speed peak. The waveform of a looseness condition will have a very non-repetitive pattern due to the random impacts as the rotor is rattling around in the mountings. During a balance job, the phase readings may be steady and then become erratic after a correction weight is applied. This is because a looseness condition existed at the beginning of the balance procedure, with the force of unbalance pulling on the rotor, holding it in a firm position and masking the looseness. Once the force due to unbalance is reduced substantially, the rotor exhibits looseness as the dominant condition, which then minimizes the effectiveness of further balancing. When performing phase analysis on a machine, remember that looseness can exhibit a directional phase of 180 degrees between components and erratic phase indicating rotating element looseness. In another program, Resonance Detection, We used a tuning fork to illustrate the fact that everything has at least one resonant frequency, and that resonance can amplify the forcing frequency by more than 10 times. Another characteristic is that the phase changes as the machine's speed is increased or decreased to pass through the resonance frequency. This phenomena of a 90-degree phase shift at resonance provides another tool to detect a resonance problem. For example, normally when the sensor is moved from a horizontal to a vertical position, there should be a corresponding phase change of about 90 degrees. However, if the phase changes 0 or 180 degrees, it indicates a directional resonance condition. The 90-degree shift due to resonance causes what should have been a 90-degree change to be either a 0 or 180-degree change. Throughout these examples, we have been ignoring the vibration amplitude. However, to determine which of these directions has the resonant condition, it may be necessary to compare the amplitudes of both readings. A good rule of thumb is, if the amplitude ratio between the two radial measurements is 1:3 or greater, it is a good indication of a resonant condition. It is not uncommon for one to be 10 or more times higher than the other. The measurement with the highest vibration amplitude is the location of the resonant condition. When this phase condition exists, then inspect the component for integrity such as cracked wells, which affect the resonant condition. There have been many instances where cracked bearing pedestals and supports have been re-welded, and upon restart, the machinery vibration returned to acceptable levels. Another indication of a possible resonance condition is erratic phase readings. Depending on the stiffness of a machine, the resonant frequency may have very little damping. This means that if the machine's speed excites a resonance, even small changes in speed drastically affect the phase, causing it to be very unsteady. If this condition is suspected, perform tests to verify whether it is resonance. In summary, resonance can be detected with phase analysis due to its phase characteristics, which can be directional or very erratic. An operating deflection shape is, as the name implies, a graphical representation of a machine's motion at operating speed. Since phase measurements provide both the direction and amount of movement, they can be used for multiple points on a machine to illustrate how it is moving. Many phase measurements are required, and they must be entered into a software program to animate the measurements. Make a grid sketch of the machine locating the specific points for making measurements. Record the phase readings for each of these points. The operating deflection shape can then be animated and turned to see how each element is moving. From this, you can get an idea of the flexing taking place in the machine. Static phase measurements can provide much information about the machine's condition, and when multiple phase data points are input into a software program that animates the data, you can actually see the movement that is taking place in the machine. Static phase measurements provide another tool for diagnosing many machinery conditions. Remember that because phase measurements provide amount and direction, they can be displayed as vectors to show the machine's motion. Use the 6-phase comparisons in the radial direction and the 6-phase comparisons in the axial directions. Be sure to take into consideration the orientation of the sensor. The directional phase comparisons, as well as some erratic phase conditions, point to specific machinery faults. All of these measurements have been using the 1 times shaft speed and filtering out all other frequencies. However, a multiple of the takt pulse frequency can be monitored by entering that number here, which then invokes a filter around that band. This feature is valuable for some applications. For example, if a horizontal measurement has a high 3 times peak, but the vertical is very low at the 3 times peak, then monitor the third order and compare the phase relationship at this frequency. There should be a 90-degree phase shift between the two. But if there is a 0 or 180-degree change between them, then a resonant condition exists. In this section, we have addressed unsteady phase and erratic phase. But there is another problem that sometimes occurs, especially on motors, and that is walking phase. A walking phase is one that moves through the 360 degrees of the circle. It is usually fairly slow, so that at first the measurement may seem fairly steady, but over the period of a minute or two, the phase has walked the entire circle. This phenomena occurs when two dominant peaks are close together, within 20 CPM, such as electrical line frequency at 3600 CPM and a shaft speed of 3595 CPM. Usually, the closer the two frequencies, the slower the phase walks. On frequencies this close, it is sometimes impossible to separate them to include only shaft speed. Another powerful analysis tool is tracking phase through transient machine conditions. Transient conditions are those that are changing over time, such as during a startup or coast down. The data collected can then be displayed in Bode plots or a Nyquist plot. The Bode plots are the amplitude versus RPM and the phase versus RPM. A Nyquist plot combines the two plots to show the amplitude and phase vector for every machine speed. The coast down data provides very good information for determining resonant frequencies because as the shaft RPM crosses a resonant frequency, the vibration amplitude is recorded as well as the phase. Details for setting up and collecting startup and coast down data are included in another program, Resonance Detection, and are not repeated here. Here we will show examples of coast downs and interpret the results. This coast down plot has two high areas of vibration that at first seem to indicate there are two resonances. However, when viewing the phase plot, the phase changed at one of the high amplitudes but not the other. Without a phase change, the machine did not go through a resonance. The high vibration at this frequency is from some other source. In areas where multiple machines are running, the high vibration could actually be from another machine. In this example, the high vibration is from a severe unbalanced condition in a nearby machine. We know that there should be a 90-degree phase change as the RPM moves from one side of resonance to the resonant frequency. Then there is another 90 degrees as the RPM continues past the resonant frequency. However, sometimes the phase plot will show a 360-degree phase change, and the amplitude versus RPM plot looks normal for a resonant condition. This occurs because two systems are in resonance at the same frequency. A typical example is when there are several machines of the same type nearby, such as a row of identical pumps or fans. A coast down may indicate a good phase shift at a particular frequency, and we would expect a high vibration at the same frequency. However, the amplitude versus RPM data does not have an increase at that frequency, but may even have a low area or hole. This indicates the presence of some mechanical damping, such as a tuned dynamic absorber. The dynamic absorber is designed to remove the vibration at a particular frequency, and this indicates it is doing a good job. When there are two phase shifts, it indicates there are two resonances in the system. Both phase shifts will be in the same 180-degree hemisphere. These Bode plots can reveal good information about the machine conditions, especially the resonance frequencies and the amplification range. The amplification range is the frequency range where the vibration is amplified due to resonance. The Nyquist plot is a polar representation of the recorded phase and amplitude. Each point is then the vector location of the unbalance amount and direction for each RPM during the coast down or startup. The loop should be 180 degrees of phase change from one end all the way around to the other, with the resonance frequency being at the halfway point. There may be other circles with a 180-degree phase change along this circle, which are other resonances in the system. To collect good phase data without holes or gaps for machines with quick startups or coast downs, increase the bandwidth to get faster samples and data. Phase data from transient conditions, such as coast downs or startups, provide information about resonant conditions and frequencies that may be difficult to acquire by other means. This information can help you in determining appropriate operating speeds and residual unbalance. Multi-channel analyzers can perform the same functions as a single-channel analyzer and more. They have the ability to track and display two signals at the same time and then compare them, even drawing a phase comparison between the two. Earlier in this program, we used a multi-channel analyzer to display the tach pulse directly on the waveform. As we roamed the machine with the sensor, we could see clearly the phase change from point to point. However, for phase analysis, probably the most powerful technique is called cross-channel phase, which allows you to use two or more vibration sensors for phase measurements. A big benefit to this is the machine process does not have to be interrupted to mark it with a reference tape or be pre-marked with the phase angles, but instead uses the actual vibration data from one sensor as the reference and compares it to the data from another sensor. Essentially, it performs the same function we illustrated with the two sine waves from the unbalanced wheels. That is, it compares the peaks for a particular frequency to determine if they are in phase or out of phase. The time difference is calculated to determine the exact phase relationship between the two. The waveform energy may seem to be very busy and intimidating for us to perform any calculations, but the analyzer can display the data as a spectrum. Then we can select a particular frequency of interest and have the analyzer display the calculated phase relationship. Notice that we can select any frequency in the spectrum for the phase comparison. Because this capability is here, there is also the ability to display the phase relationship for every frequency in a phase spectrum. This spectrum has frequency as the x-axis, but has phase in degrees as the y-axis. Now we move the cursor to a particular frequency on the reference spectrum and read from the phase spectrum the corresponding phase angle. In order to use this cross-channel phase effectively, certain setup considerations must be made. First, the two sensors must be using the same units, such as Gs. Secondly, the sensors must be in phase. That is, they must read the same phase angle for a given point. To check for this, place the two sensors side by side on a machine and check the phase between the two. They should read exactly the same or within 10 degrees of each other. Now select one sensor as the reference and the other as the roaming sensor. In some multi-channel analyzers, the X channel must be the reference. In systems using A and B channel references, the A channel typically is the reference channel. Then make the measurements, storing the data for later retrieval and analysis. With the multi-channel instrumentation, the same 6 radial and 6 axial comparisons should be made as with a single-channel analyzer. In making these measurements, two significant differences exist between a single channel and a multi-channel measurement. First, the reference is portable, that is, it may be moved depending on the need. So for a horizontal to horizontal comparison, it must be in one of the horizontal positions. And for a vertical to vertical comparison, it must be moved to one of the vertical points, and so on. The second difference is the multi-channel has the ability to look at any frequency of interest. Another advantage is the data is stored as spectral and waveform data, allowing you at your convenience to perform any analysis, including cross-channel phase, which is only one of many multi-channel functions. A case history involving multi-channel phase data to solve a vibration problem on a high-pressure centrifugal pump illustrates the value of phase analysis. The pump header repeatedly cracked, causing a shutdown of the manufacturing process. A temporary brace was installed to help remove the strain on the header, but it cracked again. No other work has been done on the machine, and the process, speed, and machine configuration were not changed. Since cracked wells are typically indications of resonant frequencies excited from some other forcing frequency, there must have been internal changes in the machine to generate a forcing frequency. Now it is the job of the analyst to determine the resonant frequency and the source of the problem. Initial data was collected on the pump body in the vertical and horizontal directions. Amplitudes in the horizontal direction on the pump housing exceeded 50 Gs. Amplitudes in the horizontal direction on the coupling end of the motor at motor shaft speed were in excess of 1.2 inches per second. The apparent problem frequency identified during this data collection process was the running speed of the motor, 59.5 Hertz. New questions now arise. Is the 1 times turning speed of the motor the cause of the problem? If so, what change occurred in the machine to cause this? Where are the resonant frequencies? Since the data indicated that 1 times turning speed was the possible cause of the problem, the decision was made to gather impact data to determine the resonant frequency. Phase data was provided using a multi-channel analyzer. The data from the impact test in the vertical direction does not coincide with the 1 times turning speed of the motor from the initial data. When the horizontal impact data was gathered, it became apparent that the 1 times turning speed was exciting the resonant frequency in the horizontal direction. In an attempt to find the changes in the machine's integrity, the analyst found a significant phase shift, 143 degrees.